This is one of the most important feature we found to make upcycling to work. No matter what the input is, the output produced should be the same as the original MLP model.
All right, welcome everybody to Archive Dives with Oxen AI, where each week we dive into interesting new research papers in the field of AI and ML. This week, we're lucky enough to have an author with us from Nvidia, Ethan He. Ethan has been working on scaling up mixture of expert or MoE models and recently popped into our Discord to share some of his recent work and including some of the open source code that went into training these models. Ethan maintains some libraries at NVIDIA, such as the NeMo and the Megatron Core libraries, so knows all about training these models at scale. And today he's going to be sharing his work on upcycling large language models into mixture of experts. And from my understanding, upcycling is a way to increase the model capacity without needing to train from scratch. So it helps us with the compute and time needed to train. But Ethan's the expert here, so I'll let him take it away. Thanks for joining, Ethan.
Hey, Ethan, could you include what is meant by capacity of the models when you give the introduction, please?
Yeah, sure.
Thank you.
I'll talk about it. Yeah, thanks for having me. So I work at the Gen AI framework team at NVIDIA. We maintain two libraries, Megatron Core, which is a core library to parallelize and accelerate transformer models at scale on thousands of GPUs or tens of thousands of GPUs. The other library is called NeMo. We maintain NeMo, which is like a zoo of recipes to train different kind of models, including ASR, LLMs, and more recently, I'm working on video generative models. I'm going to talk about our recent paper, Upcycling Large Language Models into a mix of experts. And our code is available in this GitHub link. I'll share the slides later. First, let's talk about what is MoE. So MoE mix of expert is primarily targeting the feed-forward layer of the transformer models. Traditionally, you have self-attention, residual, and also FFN layer, and another residual. So instead of having a simple feed-forward network, you replace a feed-forward network with multiple of them. Then you have a router, which produce probability to route to which either one of them. So MoE replace dense models with more parameters. That's why it has higher capacity without changing the model compute. The compute stays the same since you only active one of the expert at a time, but you have more parameters, which is usually recognized as more knowledge and more capacity. And so each token active few expert, either it's one expert, two expert, or that's commonly used. More recent, there's also more expert, like 8 experts. And the model size increase, but the model compute stays relatively small.
And Ethan is a good way of thinking about the motivation behind mixture of experts. Like I like to think of the analogy of a hospital, and you might have a general practitioner that has general knowledge, but then you might have specialized ones that are like rheumatology or pulmonary or something like that. And each one of the experts within here, so each one of these sub neural networks can learn different things, and then the routers kind of like the person at the desk routing you to the right practitioner. Is that a good way to think about it?
Yeah, that's a good metaphor. Yeah, when the patient come in, only one of the experts would take care of the patient. Yeah, that's how you increase the capacity, while the compute is the same. Like each patient still takes the same amount of time to see the doctor.
Nice. And then when you say like the compute stays the same, that's like the actual flops, but do you have to increase the memory usage to be able to have all of these
Mhm,
experts to switch
mhm.
between?
Right, theoretically, flop stays the same, but memory does increase. And we're working on various techniques to reduce that memory cost.
Cool. Thank you.
Okay, so if we dive in deep into MoE layers, there are actually four operations. The first operation is routing. It assigns the token's features vectors to expert based on the probability. Let's say the tokens are basically the number of tokens, which is sequence length by the hidden size. The router is a matrix. It matrix multiply with tokens. It produces the probabilities and the expert indices. Given these expert indices, you will need to permute these tokens into different experts. You need to sort uh, like aligns and groups them according to which expert they are activated to. Like for example, the expert 0 would have quick and fox, expert 1 would have the jumped, so on and so forth. The the third step is a computation. So you would multiply the experts with the tokens. This is the same step as the feed-forward network. The final step is on permutation. So on permutation, you need to assign them back to where they are. Basically, if there are one token, if you have more than one expert, you also need to do a weighted average of all of the tokens together to get the final results. So something notice here, they're dropping here. If you have capacity factor, which is to limit how many tokens each expert can be assigned X maximum, you will selectively drop some of the additional tokens. And some expert may get assigned less. You would pad the unused tokens.
And then, so the router's job here, since it's at the token level, is say you had um, in the hospital analogy, maybe you have a word that is very specific to a subdomain, like a complex word, and that word can get routed to the right expert. And then you're saying you could have multiple words routed to the same experts here.
Yeah, multiple words like activate the same expert. Primarily, this is for avoiding other memory, because in the usually we use expert parallelism, which means each expert resides on one different GPU. Like the memory there is constant. You would set a capacity factor to limit if there are too many tokens come into the expert, you would drop some of them in the hospital metaphor. Like too many patients are seeing the same doctor, they would only take a fixed amount of appointment.
Great.
Okay, so if we look into the router it's tokens by hidden size, and the router itself is simply a 2D matrix learnable that can produce tokens by experts. So this token by expert matrix, you can reproduce top K and probability from this. So you first take the softmax across different experts to get the probability, and then you take the top K probability from these softmax scores. In this case, I'm showing like top 2 probability. You will see that some of the experts have more tokens assigned. Some of the experts have less or even 0 tokens assigned. So this is a token imbalance problem. So if you take it from the token perspective, it is balanced. You might ask a question like why do we do the softmax on the expert axis instead of the token axis? So this is primarily because of the next token prediction nature of autoregressive models. If you take the softmax across the token axis and select top K tokens for each expert will be perfectly balanced, but you would look into the future, which means you need to have the full sentence when you're doing the softmax, which doesn't make sense for autoregressive model because they don't know the future tokens. But that makes perfect sense for vision transformers and the BERT models. Actually, those models do it that way. So token imbalance problems are only for LLMs. So here are several different cases where you can do jobless, which is a naive way. Like you don't drop any tokens. You might run into auto memory issues, or you can selectively drop the tokens. So there are two different implementations here. I won't go into the details there, but both of these options are supported in our library.
And then if you could go back to the softmax scores, is it like a hard threshold on the value, or how do you know if you drop it or not?
Um, could you repeat the question?
So for each one of these softmax scores, you have like 0.5 and 0.3 and 0.2 and 0.1 in the top one. Is it like anything over 0.3 we keep, or how do you decide which ones you keep and which
Oh,
ones you drop?
so usually people only take like top K, which is instead of top P. Top K is just a fixed number, like top one, top two. You only take the top two expert no matter the probability. It's just the highest two probabilities. Um,
And
maybe
then if you're taking the top two, then how did they get imbalanced? Maybe I'm missing somewhere there. Because if you're always taking two, then how do you sometimes get two and sometimes
yeah,
get
yeah.
three?
Yeah. So for each token, it's balanced. Each tokens are getting assigned
Mm,
to experts. But if you look at the experts, if you look at these axes, uh,
got it.
yeah. So expert one and zero have a lot of tokens, but two has no token at all. Because the way parallelism work is the tokens are usually distributed on all of the GPUs, but the experts are distributed on different GPUs. Say if you have four GPUs, 0, 1, 2, 4, 3, they are distributed on those four GPUs.
That makes sense. I was looking at it sideways, and now I see what you're talking about. Great.
Cool. Okay, so uh, we talk about the token imbalance problem. So one of the way to solve this is expert balancing loss introduced by switch transformer. This is commonly used for most of the MoEs. So if you don't have this low balancing loss, you will see the problems I previously showed. Some of the expert have zero tokens assigned. So this is an auxiliary loss that can facilitate balancing the tokens across experts during training. This is basically a weighted sum loss. Alpha is the factor to balance this with the large language modeling loss. And the F and P here, so F counts the number of tokens assigned to this expert, and P is a softmax probability. So multiplying these two together and minimizing it, the network would learn to balance the tokens across time. Okay, So let's dive into another detail in the MoE design. So this will be one of the key difference. This is one of the key difference we discovered, and is very helpful for upcycling our models. If you see on the right, this is a standard. This is a classic switch transformer style router. So here you get the input from previously the attention or layer norm, and then the router would go through softmax then top K. So the softmax probability of all of the experts would sum up to 1, and you do a top K. Usually the sum would be smaller than 1. And on the left is a Mixtral style. The Mixtral's 8x7B model introduced a different style of router, which is softmax then top K, top K then softmax. So the experts that are not in top K will not get probability assigned, and the softmax would apply to the top K experts, so they always sum up to 1 when you in the output. So the difference here is very important for upcycling, which I'll explain later.
So intuitively, it's like each one of the experts that you choose is going to get more weight assigned to them because you're only doing the softmax on less values, right?
What's the question?
So it looks like on the left, you only have 2 values that you're doing the softmax over, so you get a higher probability for the one on the left
Yeah,
than the one
yeah,
on the right. And then you're doing softmax over all of the experts on the right. So the probabilities are going to be much lower when you take the top K.
Yeah, the probability here is much lower. Another problem we see is if you do this, the problem is your probability distribution is changing across training, across different input data. So so this one, the probability distribution is always measured on all of the expert, but this dynamically change given what experts are activated, which is harder to learn.
Got it. So this makes it easier to learn as well because it's more consistent.
Yes, yes.
Yeah, makes sense.
So we found that the mixture style way didn't work as well as a classic switch transformer. Softmax and top K is still better. Here we did some experiment for both. On the left is pre-training, and on the right is upcycling loss. Like in both cases, uh, the switch transformer style router performs better. But I'll explain soon why Mixtral choose to use the reverse style router. Okay, so now we can after the introduction to MOEs, I can jump into our paper upcycling the dense models into a mix of experts. So if you're only going to remember one thing, you can remember this. You can transform any dense models in existing pre-trained dense models into a mix of experts. By continue training these upcycled models, you can achieve better accuracy than simply training the dense model further for the same number of compute. So we are talking about the regime where you already have some pre-trained dense models and you have some new data or more compute. You want to improve your dense models. So upcycle operations would convert these dense models into MoE. And this is this can perform much better than like keep training the same dense models further for the same number of compute.
So concretely, you could take something like Llama 8B and then convert it to a 8 by 8B by copying all the weights and making it a mixture of experts. Is that kind of the intuition?
Exactly, exactly. So instead of a Llama 8B, we're doing it on our own model, which is Nemotron 415B. Yeah, you can see here is a simple table shows the results first. So Nemotron 415B is our base model, and the continuous training version just keep training the dense models on some of the new data. We have 1 trillion new tokens. And instead of doing continuous training, you can do upcycling instead. So here are two variants which I'll explain later, but they all improve the MMLU and the validation loss in roughly like 4 to 5%.
Wow, that's a big jump, and it's on the same amount, so it's like 1 trillion tokens for all of these continued
Yes,
training. Cool.
yes.
How does this improvement translate into cost?
Translate into cost. You mean the cost to train the models or
Yes.
the cost to
Yeah.
inference? Yeah,
I was thinking training, but inference too, maybe.
yeah. So here is a let's talk about cost to inference first. So here are two variants. I'll explain later, but this variant have the same cost to inference, and this variant have double the cost to inference because it has double the compute. Uh, about the cost to train, it depends on the number of tokens. For for the same flop for version of the MoE, it's the same number of compute as continuous training. If you compare it with pre-training, pre-training we train on 8 trillion tokens, so 1 trillion is only roughly 13% of that. So, it's relatively cheap compared to pre-training such MoE models from scratch. Yeah, originally we thought about pre-training these MoE models from scratch. This is one of the reasons why we do upcycling, which is much cheaper to get an MoE model.
Thank you. Although I guess you work at the wealthiest company in the world for compute, so maybe it maybe you're not as scrutinized as everyone else might be.
We we are also lack of compute because we sold all of the GPUs to other companies.
Yeah,
That's funny.
yeah. I can see like the Nvidia financial inspector coming around saying, Ethan, you're costing too much.
Yeah, I'm trying to reduce the cost exactly here. Otherwise, it would be like 8 times the cost.
Yeah, you're the accountant's hero at Nvidia.
So, so this figure explained how the upcycling works in, so we didn't invent upcycling. Upcycling is in one Google's paper a long times ago. This is how you upcycle the model. You so on the left is a plain old transformer models. We only put the dense layer here and omitted the attention layer. So the dense MLP layer is copied into multiple of them. Here I only show two expert. And so this is two expert top one, and the router width is randomly initialized. This is how this is how you upcycle the model. Quite simple, right? And we now we can revisit like how to what's the difference um, between the Mixtral style router and the switch transformer style router after you upcycle model. Well, basically, after you upcycle this model, you can just keep training these models on the new data. and you should expect them to converge very fast because you have the original model weights. One of the key factor here is once you convert, when you convert this model into MoE, you want to maintain the model, you want to maintain the model functionality in the first forward pass. When I say the functionality or functionally the same, it means when you after you convert the model weights, no matter what the input is, the output produced should be the same as the original MLP model. This is one of the most important one of the most important feature we found to make upcycling to work. For example, here the case is the MLP layers are copied here, and the probability is multiplied on the activate expert. You will see the problem with switch transformer style router because we just mentioned the probability doesn't sum up to 1. We have 0.4 and 0.2 selected. The probability is smaller than 1, which means the MLP multiplied by the probability, the output scale is also smaller than 1, given that the MLP layers are simply copies of the original dense model. And this is how Mixtral 8x7b solves the problem, because they switch the order of the top K and softmax. The probability sum within top K is always 1. And given the MLP layers are the same, the output produced by the model is exactly the same as the original dense model. This is very important because when you continue to train this model, these upcycled MoE models on new data, you will start with a very low loss, and the model converges extremely fast. Otherwise, there will be some catastrophe forgetting problem, which is as if you're training from scratch. Is this part clear? Because this part is one of the key idea.
So I think when you were talking earlier, you said that the switch transformer way performed better, but you're saying when upsampling, swapping the softmax and the top K works better. Is that correct? Or did I get it backwards?
Yes, that's correct. That's
okay.
correct. So,
Cool.
so this is how the Mixtral style router made it work. But from our earlier experience, I demonstrated that in pre-training, the Mixtral style router perform worse than switch transformer style because the router probability is dynamic distribution on top K instead of all of the expert. So this is kind of like a compromise for upcycling. And we don't want this compromise. We want as good performance as per training.
Yeah, that makes sense.
So actually, there's a very simple solution to this. We propose to do with scaling. Since the top K probability summed up is smaller, we can simply multiply a factor to the output, or in this case, we multiplied it on the MLP layer. Assuming uniform distribution here, if you have 8 experts, the probability of each expert would be roughly 1/8. So this is a very strong assumption. We verified it on most of our models, which is actually this case. In the beginning of the training, if you randomly initialize a router, the probability is pretty uniformed. So this assumption is safe. And so each expert have the probability is 1/8. If you select 2 experts in this case, The summed probability is 1/4. So we simply multiply the MLP layer by 4. So this will maintain the key feature that the output is the same as this model. So this is very important for models up more than 1 billion parameters. In the original Google paper upcycling, they weren't able to upcycle models beyond 1 billion 1 billion parameters with some difficulties. We're guessing this is one of the reason that it's not scalable, because on larger models, it's very hard to recover like the scale difference when you start training. It will lead to catastrophe forgetting.
Is this also related to the normalization and the loss that you showed before to try to balance which experts are being used in the router?
And which normalization?
When you were showing the loss function before, you were
Oh,
doing,
the loss function.
yeah,
Uh, so the loss function is separate. So that one it is for training. So it's another topic there. During training, you want these experts to be balanced. Otherwise, you might have some of the expert dead, uh, and they won't receive any tokens at all during training.
got it. But does it help if they're balanced to also make that assumption that you can just multiply by 4 because they're more balanced?
Yeah, it would help a bit in the beginning of the training. Uh, yeah.
Cool.
So with this simple trick, we're able to get better accuracy when we upcycle the model compared to Mixtral style router. So we trained two models previously. I show the number here. So on the right, this is upcycling. If you do a Mixtral style, the Mixtral style is a green line, and if you do the switch transform style router with our scaling factor, the loss is slightly lower than Mixtral style. If you don't do this, it will lead to catastrophe forgetting, and the loss is as if it's random, which is like it would start from somewhere like 12 and slowly going down. So another key innovation is fine-grained MoE. We so recently there are a lot of MoE models that use more experts but smaller ones. They compensated for that by route to more expert. So this is fine-grained, and because you have more smaller experts, and you get the flexibility to route to more experts. Here I'm giving an example, like on the left is our plain mix of two expert top line. And this is uh, equivalent in the sense that the compute is the same and the parameter is the same, the fine-grained model. We call this E2, G2, T2. So E2 is an expansion factor. Its expansion factor is 2, means the MLP layer is copied 2 times. And G2, G stands for granularity. It's the expert size, how many times it decreases. So here the expert is decreases by 2. You segment each MLP layer in the intermediate dimension by 2. The intermediate dimension, we segment the intermediate dimension because the input hidden size and the output hidden size can stay the same. It's only the intermediate projection part gets smaller. So this would maintain other part of the network unchanged.
So it's kind of like you cut the parameters in half. for
Yes.
this one to get more experts.
Yeah,
Yeah,
exactly.
cool.
So the top
And then is
T,
there a intuition between why more experts but smaller would be better versus less experts but bigger?
yes, the intuition is a combinatory problem. So if you have more expert, you have more flexibility to select the different experts. For example, at Conza Life, you only have your mixer of two expert only have two modes. You can only select one of the two. But on the right, we have four experts. So it's four expert. You're choosing two out of four. So you have 12 you have 12 different combination to select from. This is also the case for like the normally use eight experts. Expect eight expert top two, you only have 56 options, 56 modes. But if you have fine grained, you have much more different combinations. So the model is more expressive.
Cool, that makes sense. Thank you.
Usually, T equals to G. This is because uh, G shrinks the parameters. If you want to maintain the network compute to be the same as a dense model, usually T is equals to 2 because you just route to 2 expert to compensate for the decreases in size.
Cool. So E is the number of times you copy it, G is the number of times you cut it in half, and T is the top K.
Yes, yes. So this is very popular most recently, especially in models like um, DeepSeek, MoE, and the Queen 2.5 models. Like DeepSeek have 164 experts, and the Queen 2.5, I think they have like 64 experts.
Wow. Yeah, the Quen 2 is leading a lot of the leaderboards in coding, right?
Yeah, yeah.
Cool.
So you'll notice like upcycle this model, upcycle these fine-grained models is much more difficult. Um, so here the difficulty is we can no longer maintain the key feature that the output is the same as the original dense model. So on the left, the transformer layer, the MLP, it has the input projection and output projection. So we are segmenting the intermediate dimension, and the hidden dimension stays the same. Here I'm segmenting this into like a G equals to 2, so I'm segmenting into two parts. The different color like represent two different shards. So you'll notice when I shard this and then copy this because E equals to I copy this into two shards, you get different expert instead of the same expert in the beginning. Because in the traditional upcycling case, you simply copy the MLP layer. All of the experts are the same. But here you actually have two sets of different experts because they're from different shard. And the challenge here is to maintain the property that in the first forward pass, the model is functionally the same as the original model. You will need to route exactly to one of each shard. Here I highlighted in red. So only in this way you can maintain the properties that this stays the same. The output function is the same as the original dense model. But the router usually is pretty much random. You cannot we randomly initialize the router, so you cannot choose like which expert it select. In the beginning, we try to do some kind of hard grouping. where we simply like force a grouping of the different expert groups. We simply like have two router groups. One of the router group like have top one out of two, the other same case. So you always route to one of the two expert. But this would change the model architecture and make it more difficult. It makes the model less expressive because you're forcing the model to choose one of the two. Here we introduce a very simple approach to tackle this challenge. So instead of hard grouping, we introduce a virtual grouping, where instead of randomly initialize router weights, we initialize half of the router weights, then duplicated. So in this way, the router weights are duplicated, so no matter what the input hidden tokens are, you're always producing the same probability among these two groups in the first iteration. So, so when you take the top two, there are always two probabilities that are the same from the two virtual group. If you pay, and in this case, you would always pick one expert from each group. However, during training, this probability will gradually fade away and kind of smooth in. So this is only enforced in the beginning of first few iterations because of the router weights are initialized this way. But as you train, this constraint is gone.
And
It's
then I think you said the router weights are initialized randomly at the start. So
yes.
if they're random, then why does why do these virtual groups help? It's just they're the same random.
Yeah, they are the same randomness because we duplicated here.
Got it.
Because they are random, but the weights are the same across these two shards. No matter what the input you multiply, the output you get are the same for these two group, right?
Yep. Yep. That makes sense. So it's really just you do the randomization once, make two copies of
Yes.
it rather than doing the randomization twice.
Yes. Yes.
Makes sense.
As you continue to train the model, this property would fade away because router weights are getting updated. Okay, so this is a formula for upcycling the fine-grained MoEs. I put it here, but quite complicated. You can look at it in the paper. For the experiment, we did the experiment on Nemotron 8 trillion tokens, and the ablation studies on the Nemotron 2B models. For scaling up, we did it on the 8 by 15B models on 1 trillion tokens. So this is the first paper that revealed like how to upcycle big models beyond 1 billion tokens, 1 billion parameters and 1 trillion tokens. We found that actually learning rate is still the most important hyperparameters to train, even for upcycling, which is especially the case. So on the right, you can see different learning rate schedule. Traditionally, if you continue to train a model, you usually use a very small learning rate. So this small orange learning rate is the minimum learning rate from pre-training. This is also how we did continued training, because it's a smooth transition. The loss will stay relatively similar to pre-training, and you're just keep improving the model. But you can see actually for upcycling, if you increase the learning rate, the loss are actually getting better. The hypothesis this is because when you upcycle the model, the architecture is changed. You need the model to find a different local minima. And the higher learning rate helped the model to find a better local minima.
Cool. So even though it looks like it's way worse at the start with the higher learning rate, that's just because you're kind of reinitializing the weights to be new experts, right? So you kind of want to
Exactly.
change the weights more drastically.
Exactly.
I
Cool.
think, Greg, I think that's what I saw also when I was training um my model for emotion detection.
Oh
And I
yeah.
actually I think this yeah, I think this was where I ran out of when Google CPU charges got me and turned me off. But um yeah, I think this with tweaking the learning because it took so much longer to complete
Nice.
Interesting.
changing the learning rate.
Yeah.
Nice.
Took forever.
I'm glad to hear that.
I'm trying to pull up my presentation, but I'm pretty sure I saw the same thing.
Nice.
So we did some interesting analysis of the weight similarity here. So the similarity is simply the cosine similarity between the original weights and the upcycled model. So this include all of the layers, attention, expert, layer norm, everything. The cosine similarity between 0 and 1. So if you use a constant learning rate, you will get the cosine similarity, which is almost 1, which means the model didn't deviate much from the original model. But if you use a higher peak learning rate, as we shown before, the cosine similarity is much lower. Uh, and we found this to be one of the important metric which is coincides with the training loss. So if the constant similarity is pretty high, upcycling loss is not very good either.
Oh wow. That's a clever way of seeing whether the experts are learning different things or not. I hadn't thought of
Yeah,
that before. That's cool.
yeah. If the constant similarity is the same, which means pretty much the experts are the same as each other, then why not use a dense model? Yeah.
Yeah, totally.
So, so interestingly, we did some data analysis between the Mixtral 8x7B versus Mistral 7B. So, their constant similarity is also around this area, which indicate like they also upcycle with a high learning rate. Um, which is what they didn't reveal in the beginning of their model release. And we also measured some other models like Llama Instruct versus Llama Base. Also found that Llama Instruct actually have very high constant similarity, like almost 1, versus a Llama Base. So this is a common case for continual training or alignment because the learning rate you use it's not very much different, not very much different from the minimum learning rate. And this is a model, it's still very similar to the base model.
So you're saying even when you're going from a base model to an instruct model, this is a useful tool to see how much it's actually learned.
Yeah, it will be an interesting indicator. But usually
Yeah.
for, I'd say for if the model architecture is the same, you probably don't need to change the learning rate, increase the learning rate too much. But some moderate amount would be useful, especially when you have more data. For alignment, it's not like 1 trillion tokens in our case. So that when you have less data, you probably need lower learning rates. More data
Mm.
or different model architecture would need higher learning rate.
And then were these mixture of experts all trained off of the base model, or did you do any instruct models that had already been instruct tuned?
We haven't done any instruction training, so this is all base model. So this
Got
is
it.
continual training. Yeah.
Cool.
So we also did some additional experiment where to upcycle the model into fine-grained MoE. and it's pretty effective method, and we found diminishing return beyond 64 expert. So 64 or 128 is kind of the limit for fine-grained MoE, which is also used in the Coin 2 model, which use 64. Okay, so finally we can revisit the scores, like the MMLU and the validation loss. Previously we explained EG and T. So here EAG T8, it has 64 expert and top 8 selection. So this one, the training and inference computer is the same as continuous training. So this one, the validation loss, it increased roughly 4% and the MMU roughly 3%. And the EAG1 T2, this one is a traditional MoE where you have 8 experts, top 2. So this has roughly 70% increase in compute because you're selecting 2 expert, and the 2 expert are the same size as the original dense model. This have better improvement, sacrificing some extra compute overhead. The validation loss increased roughly 5% in this case. So to contextualize like how good these improvements are, we can plug in the classic scaling law paper from OpenAI. So if we're not increasing any flops, which is a EAGA-TA case, it's roughly as powerful as 1.7 times bigger dense model. And the EAG1 T2 model, which has a 70% increase in compute, is roughly as powerful as a 2 times bigger model. So the result is quite interesting because we only spend like 1/8 compute of pre-training, but we are achieving like 1.7 times bigger model performance. So this means like upcycle these dense models into MoE is a way to save compute.
Wow, so it looks like that even would make the scaling laws better. Like in theory, if we have the same size model with more data and you use this approach, you're going to get even better scaling laws. But I guess there
Yeah.
hasn't been. Uh, has there been an experiment past the trillion tokens, or is that the biggest data set we've done?
So 1,015,000,000,000B, it's a lot of compute for us already. This
Yeah.
is the biggest experiment we've done. But yeah, we
How
are
long? How long does that take to train in like days?
so this is 0.3 Utah flops. Utah flops, it's to contextualize it, I think it's roughly like 500 GPUs for a week or something.
500 GPUs for a week. Okay, got
Yeah.
it.
So yeah, this is as you described, this kind of lives on a different scaling law curve than the dense model. Um, it's an interesting direction we're exploring next, like what the scaling law looks like in this case. I think that's pretty much my presentation.
Cool.
Thank you.
And I'd be curious, are you applying any of these MOEs to the video generation work you're working on?
Oh, yeah, it will be very interesting to see how they work on videos, especially because it doesn't have the autoregressive next token nature, the
Hmm.
causal nature, so we don't have the token imbalance problem. Yeah, I'm very excited to see what would happen there.
And then have you done any upscaling with BERT-like models bidirectional? Because they would have the same property of not needing the autoregressive.
All right. Not yet, but I heard people have done that, and it's better. Yeah.
Cool. Any other questions from people in the chat? All right. Well, thank you, Ethan, for. Oh,
Hello?
do we have one? Yeah.
Hello? So if I'm getting this right, this model is, so basically it has, how do I say it? Hold on. So the purpose of this model is to like give it more variety of expertise.
What's the question? Give it more
Like,
what?
this model, you split the feed forward so that it has more expertise on specific part of the task.
So
Both, I think it's both more expertise and more efficient.
Yeah,
Yeah.
yeah.
In
So for some specific expert, for some specific task, it's more efficient while being more kind of like expert of it.
yeah,
Yeah.
I'd say it's in general a much powerful
Oh,
approach than continued training.
oh, yeah. So it's making the model less general that, but more expertise on. Uh, so okay, I wanna ask for the training part. Uh, we can just not snatch off like a pre-trained model, then we just copy the feed forward, then it will adjust itself during the training.
Um, yeah, this
Yeah.
is how upcycling work. Yeah, you
Oh, I
copy
see.
the MLP layers. Like after you pre-train for a val. In our case, we pre-train 8 trillion and then 1 trillion tokens we copy the MLPs. Also,
I see.
I'd say like the experts it's this is called a mixer of expert, but this is kind of a misleading concept. It's not actually like specialized. It's the model
Mm.
itself is still very general.
It's still general, but during some specific tasks, it's more efficient and effective.
Yes. Yes.
Yeah.
Oh, I
Cool.
see, I
And
see.
I think we have time for one more question from Alex, and then we'll call it a day.
Okay,
Thanks,
thank
Shira.
you.
Yeah, I had some comments about the diversity of the experts. Since here, Ethan, you only tried it on Metrotron, and I was wondering if you could possibly, or what would you expect if you try to use a set of different diverse experts? For example, you can use a mixture of Metrotron, Llama, or Mixtral, or even like a video transformer based expert.
Yeah, that's a very interesting direction. Like you want to mix different models, as am I understand it correctly?
Correct. Yes.
Yeah, so that's I think that's actually called a mixer of model or something. It's not mixer of expert. But yeah, that's actually one of the interesting approach, and I've seen people exploring it. So they train a router to route to different models. So there's no model surgeries inside the model. Like depending on the query, they can route the query to either like OpenAI API or Anthropic API, things like that. It is more powerful. Yeah.
Interesting. Cool. Well, feel free to hop into our Discord to ask any more questions of Ethan. It was great, the presentation today. And if you could share the PDF as well in the Discord, that would be awesome, Ethan.
Sure, sure.
Thanks, everybody. Happy
Thanks,
Friday. We'll
Greg. Thanks,
see you
Scott.
next week.
Thanks for having me.